Megawatts on your mind from LIGHTHIEF. We build it, we run it, we know what works, real projects, real returns. The renewable energy podcast that doesn't waste your time. Let's go.
If you've been following along, you know we've spent considerable time discussing solar farms. How to maintain them, how they're built, what matters for keeping them running. Today we're talking about something related but fundamentally different. Something that's simultaneously the future of renewable energy, and the thing that keeps O&M managers awake at night, wondering if their fire suppression systems are properly maintained. Let me be clear from the start. Energy storage O&M is not solar. O&M with batteries added on. It's a completely different discipline requiring different skills, different safety protocols, different equipment, and frankly, a different mentality about risk. With a solar farm, if you make a mistake, you might lose some production. Equipment might fail. It's economically painful but rarely dangerous. With battery storage, mistakes can result in thermal runaway, fires, toxic gas releases, and genuine danger to personnel. The stakes are considerably higher. But despite these challenges, or perhaps because of them, energy storage is absolutely essential for Europe's energy transition. You cannot have a grid dominated by intermittent renewables without substantial storage capacity. It's not optional. It's not a nice to have. It's fundamental to making renewable energy actually work at scale. The European market understands this. Battery storage deployment is accelerating rapidly. Europe added over 9 gigawatt-hours of storage capacity in 2024, and projections suggest this could triple or quadruple by 2030. Every major solar and wind developer is now looking at storage. Existing renewable projects are being retrofitted with batteries. Standalone storage projects providing grid services are becoming common across Germany, the UK, Italy, and increasingly in Central and Eastern Europe. This growth is creating an entirely new sector within renewable energy, O&M. People who understand battery chemistry, thermal management, fire suppression, degradation mechanisms, and the unique operational challenges of storage systems. It's a specialty that requires knowledge of power electronics, electrochemistry, thermal engineering, and serious safety management. Today we're going to explore what makes energy storage O&M fundamentally different from solar or wind maintenance. We'll discuss the technologies, the safety considerations you absolutely cannot ignore, the degradation mechanisms that affect your economics, and the operational strategies that determine whether you make money or lose it. We'll talk about why storage is essential for grid stability across Europe and what the future looks like. And I'll be honest about the challenges because there are substantial challenges, but also about the opportunities because the European storage market over the next decade represents tens of billions of euros in investment and ongoing O&M revenue. Shall we begin? And perhaps check that our fire extinguishers are properly maintained before we do. Before we dive into technical details, we need to understand a fundamental difference in how we describe solar farms versus energy storage systems. This isn't just semantics. It reflects the fundamentally different nature of these technologies. A solar farm is described by power, megawatts. A 10 megawatt farm means that in optimal conditions, it can produce 10 megawatts of power at any given moment. It's like saying a car has 120 horsepower. We're describing how powerful the engine is, not how much fuel the tank holds. An energy storage system requires two parameters: power and capacity. Power, measured in megawatts, is how quickly the storage can charge or discharge. Capacity, measured in megawatt hours, is how much energy the storage can hold. It's like a car. You need to know both the engine power and the fuel tank size to understand what it can do. Practical example, a 10 megawatt, 20 megawatt hour storage system. What does this mean? The system can discharge at 10 megawatts for 2 hours, or at 5 megawatts for 4 hours, or at 20 megawatts for 1 hour if the electronics allow it. The ratio between power and capacity determines what the system is optimized for. This brings us to a crucial concept: C-rate. C-rate is the ratio of power to capacity. Our 10 megawatt, 20 megawatt hour system has a C-rate of 0.5 C. It needs 2 hours for a full charge or discharge cycle. A 10 megawatt hour system is 1 C, 1 hour per cycle. A 10 megawatt, 5 megawatt hour system is 2 C, 30 minutes per cycle. Why does this matter? Because different applications require different C rates. Energy arbitrage, buying cheap electricity at midday, selling expensive electricity in the evening, benefits from lower C rates and longer discharge duration. Frequency regulation, rapid response to grid fluctuations, requires higher C rates and short but intensive discharge capability. This leads us to a fundamental difference between solar and storage. A solar farm produces energy, it's a source. Storage only holds and releases energy, it's not a source, it's a buffer, but an extraordinarily flexible buffer that can respond in milliseconds, something no coal or gas plant can match. One more critical metric for understanding storage: round-trip efficiency. This is the percentage of energy you get out relative to what you put in. Modern lithium-ion systems achieve roughly 85 to 90% round-trip efficiency. If you put in 100 megawatt hours, you get back 85 to 90 megawatt hours. The difference, 10 to 15%, is losses, primarily heat generated during charging and discharging. Why does this matter for O&M? Because those losses must be managed. 10% of 100 megawatt hours is 10 megawatt hours of heat. That's roughly 36 gigajoules of thermal energy that needs to be dissipated. If cooling systems aren't working properly, temperature rises, efficiency drops, battery lifetime decreases, and in extreme cases, you risk thermal runaway, uncontrolled temperature increase leading to fire. Which brings us directly to the anatomy of an energy storage system. Because to effectively maintain something this complex, you first need to understand how it works and, more importantly, what can go catastrophically wrong. An energy storage system isn't just a big battery. It's a hierarchical system consisting of thousands, sometimes millions of individual cells, organized into progressively larger structures with sophisticated management, cooling, safety, and control systems. Let's start at the bottom. The individual lithium-ion cell. This is a cylindrical or prismatic cell, typically with a nominal voltage around 3.6 to 3.7 volts and capacity from 2 to 300 amp hours depending on type and size. The most popular formats are cylindrical, 18,650 to 18 millimeters diameter, 65 millimeters long, familiar from Tesla's early battery packs. Newer formats include 21,700 and the massive 4,680 cells used in Tesla's latest vehicles. Each cell has several critical parameters. Voltage varies with state of charge. Capacity determines how much energy it can store. Maximum C rate defines how fast you can charge or discharge it. Operating temperature range is typically -20 to +60 degrees Celsius. Cycle life indicates how many charge-discharge cycles before capacity drops below 80% of original. Cells are combined into modules. A typical module contains dozens to hundreds of cells connected in series and parallel to achieve desired voltage and capacity. A module might have 40 cells in series, giving roughly 150 volts, and 5 in parallel, multiplying capacity by 5. Modules are enclosed with thermal management systems, cooling plates or air channels. Modules are assembled into racks. A rack is a vertical or horizontal structure containing several to dozens of modules, with its own BMS, battery management system. The BMS is the brain of each rack, monitoring voltage, current, and temperature of every module, balancing charge between modules, protecting against overcharge, overdischarge, and overheating. Racks are placed in containers. A standard 20-foot or 40-foot shipping container can hold dozens of racks, providing total capacity from half a megawatt hour to 3 megawatt hours or more. But the container isn't just batteries. It's a complete system containing transformers, inverters, cooling systems, fire suppression, monitoring systems, and access controls. The cooling system is one of the most critical elements. Lithium-ion batteries are temperature sensitive. Too cold and capacity drops, too hot and lifetime degrades, and in extreme cases, thermal runaway occurs. Most systems use precision air conditioning, maintaining temperature in a narrow range, typically 20 to 25 degrees Celsius. Some advanced systems, like those from manufacturers such as Lin-Yong, incorporate liquid cooling for more precise thermal control, which is particularly important for high-power applications. Fire suppression is another crucial element. Lithium-ion batteries, while safer than their old reputation suggests, can still catch fire due to damage, overcharging, or manufacturing defects. Smoke and heat detection. automatic extinguishing systems, often aerosol or gas-based because water and lithium-ion don't play well together, local and remote alarms. All of this must work with millisecond precision. The PCS power conversion system is equivalent to a solar inverter but significantly more sophisticated. It must convert DC battery power to AC for grid connection and do this bidirectionally, charging and discharging. It must maintain perfect power quality in sine wave, frequency, power factor. It must respond in milliseconds to control system commands. This is high-end power electronics. The transformer steps up voltage from container level, typically several hundred volts AC, to grid level, often 15 or 20 kilovolts. Similar to solar farms, but with added complexity, power flow is bidirectional. The EME's energy management system is the brain of the entire installation. It decides when to charge, when to discharge, at what power levels, for how long. It analyzes electricity price forecasts, weather forecasts if the storage is paired with solar or wind, battery state of health, and grid operator commands. It optimizes operation to maximize revenue while extending battery lifetime. This is sophisticated software often incorporating AI and machine learning algorithms. SCADA, Supervisory Control and Data Acquisition, allows remote monitoring and control. Every parameter of every cell, module, and rack is logged and visualized. Real-time alarms, remote shutdown capability in case of faults. Integration with grid operator systems. The entire installation is enclosed in a secured perimeter with security systems similar to solar farms. Fencing, gates, cameras, sensors. But with an additional layer, strict access control. Lithium-ion batteries at this scale are potentially dangerous. Unauthorized access could lead to theft, sabotage, or accidental triggering of thermal runaway. Now, the critical question for O&M personnel: what can go wrong and how do you detect it before it becomes a problem? The list is long and rather alarming. Cell degradation, natural, inevitable, but must be monitored. Every cell loses capacity with each cycle. But some degrade faster: manufacturing defects, overheating, excessive discharge. The BMS must detect this and balance accordingly. If not, weak cells become weaker, eventually failing. Voltage imbalance between cells. In an ideal world, all cells in a module have identical voltage. In reality, there are always differences. Small differences, a few millivolts, are normal. Large differences, dozens of millivolts, indicate problems. The BMS must actively balance, transferring charge from stronger to weaker cells. If balancing fails, imbalance grows, leading to overheating of weaker cells. Cooling system problems, the most common cause of serious failures. Air conditioning breaks down, filters clog, channels block. Container temperature rises. Batteries lose efficiency, lifetime decreases, and in extreme cases, thermal runaway occurs. Technicians must regularly check temperatures of all modules, compare with nominal values, detect hotspots. BMS problems: sensor failures, software errors, communication issues. The BMS is a critical safety system. If it's not working properly, batteries can be overcharged, over-discharged, or overheated. Technicians must regularly test the BMS, verify all sensors are functioning, ensure communication between modules is stable. PCS problems: similar to inverter issues in solar farms, but with worse consequences. Damaged IGBTs, cooling problems, control software errors. A malfunctioning PCS can damage batteries, irregular charging, harmonics, voltage spikes. Technicians must monitor PCS efficiency, power quality, component temperatures. This brings us to the crucial question: how different is storage O&M from solar farm O&M? Quite dramatically different, as it turns out. If you're an experienced solar farm O&M technician thinking that energy storage is just adding batteries to a familiar equation, I have unfortunate news. Storage O&M is a fundamentally different world, requiring a different mindset, different skills, different tools, and above all, a completely different approach to safety. Let's start with the biggest difference: hazards. A solar farm has DC voltages up to 1,500 volts that must be respected. But panels don't explode. Inverters don't spontaneously combust. Mounting structures don't emit toxic fumes. An energy storage system can do all of these things. Thermal runaway is the nightmare scenario for every storage operator. It's a chain reaction in lithium-ion batteries where one damaged cell overheats, its temperature rises uncontrollably, spreads to adjacent cells, and within minutes, an entire module or rack is in flames. Temperatures can exceed 1,000 degrees Celsius. Smoke is dense, toxic, containing hydrogen fluoride. Water is ineffective and dangerous for extinguishing. This isn't theoretical, it's happened in storage facilities worldwide. Case study from South Korea, 2019. A series of fires in energy storage systems. 23 incidents over 2 years. 1 fatality, a firefighter responding to a storage fire. Investigation revealed a combination of causes: inadequate cooling, BMS errors, cell manufacturing defects, inappropriate fire suppression systems. The result: complete reorganization of safety standards for storage across South Korea. This leads to the first fundamental difference in O&M. Safety protocols are an order of magnitude more stringent. Access to battery containers requires special procedures. Before entry, gas concentration measurement, temperature verification, ventilation system check. During work, continuous atmospheric monitoring, readiness for immediate evacuation, breathing equipment within reach. After every intervention, detailed protocol documenting every action. Personnel training is the second fundamental difference. A solar farm technician needs electrical qualifications, working at height certification, basic health, and safety. That's sufficient. A storage technician needs all of that plus specialized training in lithium-ion chemistry, certification for potentially explosive atmospheres, advanced fire safety training, BMS system courses from specific manufacturers, often battery manufacturer certifications. In practice, this means you can't simply transfer technicians from solar O&M to storage O&M. They're different specializations requiring different competencies. Some O&M companies in the US tried this approach around 2018 to 2020. The result: a series of incidents, financial losses, and, in several cases, serious personnel safety risks. The market learned quickly: storage requires dedicated teams. Diagnostics is the third fundamental difference. In a solar farm, diagnosis is relatively straightforward. Thermal imaging shows overheating. I/V measurements reveal module problems. SCADA data shows underperformance. Most problems are visible or easy to detect. In storage, most problems are hidden deep within the system hierarchy. A degrading cell in the middle of a module, in the middle of a rack, in the middle of a container? You won't see it with the naked eye or simple thermography. You need advanced BMS data analytics, trend monitoring of every cell over months, algorithms detecting anomalies. This leads to the fourth difference. The role of AI and big data is far more significant in storage than solar. A typical 10 megawatt, 20 megawatt hour storage system might contain 50,000 to 100,000 individual cells. Each cell is monitored: voltage, current, temperature every second. That's millions of data points daily. A human cannot manually analyze this. You need AI systems detecting anomalies, predicting failures, optimizing charging strategies. Real-world example: a 20 megawatt hour installation in California. An AI system detected that one rack had slightly elevated operating temperature, on average half a degree higher than others. To a human watching dashboards, this would be invisible in the noise. But the AI noticed the trend. Inspection revealed one fan in that rack was operating at reduced capacity. Not a failure, just partial bearing degradation. Replacing the fan cost $500. Had the problem gone undetected, it could have led to rack overheating, module damage, cost tens of thousands of dollars. Fifth difference: cycle frequency and its impact on degradation. A solar farm has one cycle daily. Sun rises, panel produces, sun sets, panel stops. Simple. Storage can have dozens of microcycles daily. Charge, discharge, depending on application and operational strategy. Each cycle stresses the battery. Managing these cycles to maximize revenue while extending battery lifetime is an art requiring sophisticated optimization algorithms. This leads to the sixth difference: significantly shorter system lifetime for storage versus solar. Solar panels last 25 to 30 years with minimal degradation. Lithium-ion batteries in utility-scale installations typically have 10 to 15 years under intensive use, 20 years in optimistic scenarios. This means end-of-life strategy, second-life applications, and recycling must be planned from the beginning. Seventh difference, O&M response must be significantly faster. A solar farm can be down for a day or two without dramatic consequences. It loses production, but that's a linear loss. An energy storage system participating in ancillary services markets, particularly frequency regulation, may have contracts requiring 98 to 99% availability. Unavailability for a few hours can mean penalties reaching tens of thousands of euros. O&M response time must be measured in minutes, not hours. Case study from the UK. A 20-megawatt storage system participating in enhanced frequency response. The contract required response within 1 second to national grid commands and minimum 98% availability. One PCS inverter failed in the middle of the night. Automatic backup didn't engage. The system was offline for 4 hours until a technician arrived and manually switched over. Contractual penalty £20,000, plus lost revenue another £10,000. Total £30,000 for 4 hours of downtime. This enforces an eighth difference. Redundancy and backup are critical. Storage systems often have double or triple critical components. 2 independent PCS units, 2 cooling systems, backup power for control systems, redundant communications. This increases capital costs but is essential for maintaining high availability. Ninth difference, cybersecurity is even more critical than in solar farms. An energy storage system connected to the grid, responding in milliseconds to commands, could be weaponized against grid stability. A coordinated attack on multiple storage systems, forcing them to simultaneously discharge or charge, could destabilize a regional or even national grid. This isn't paranoia. Simulations conducted by the U.S. Department of Energy have shown this is a real threat. 10th difference, warranty management is significantly more complex. Battery manufacturers provide warranties for specific cycle counts or capacity degradation thresholds. But what counts as a cycle in practice? 1 full cycle? Are 2 half cycles 1 cycle? Are 10 microcycles at 10% depth 1 cycle? Different manufacturers have different definitions. The O&M operator must meticulously document every cycle, every discharge depth, every operating temperature to prove warranty claims should be honored. All of this leads to a fundamental conclusion. Energy storage O&M is a separate, specialized industry. It's not an extension of solar O&M. It's a new discipline requiring new skills, new tools, and a new mindset. Companies that understand this early will have significant competitive advantage as the European storage market explodes over the next decade. Not all energy storage systems are the same. Depending on application, location, technical requirements, and economics, different technologies and configurations are used. Understanding these differences is crucial for knowing how to maintain each type. The most common type, particularly in new installations, is lithium-ion batteries. Same basic technology as your phone and laptop, just scaled up thousands of times. Lithium-ion offers the best balance of parameters. High energy density, high round-trip efficiency of 85 to 95%, long cycle life of 3,000 to 8,000 cycles, fast response time in milliseconds. But lithium-ion is a category containing many different chemistries. NMC, nickel manganese cobalt, is most popular, offering good balance of energy density and power, used in most utility-scale storage. LFP, lithium iron phosphate, has slightly lower energy density but higher thermal stability and longer lifetime, gaining popularity particularly in China and increasingly in Europe. Some manufacturers, including companies like Linyang with their advanced LFP solutions, are pushing the boundaries of what's possible with this chemistry in terms of both safety and performance. NCA nickel cobalt aluminum has high energy density used by Tesla. LTO lithium titanate has low energy density but very long cycle life, up to 20,000 cycles, used in applications requiring frequent cycling. Each chemistry has different characteristics, different operational requirements, different degradation profiles. O and M personnel must know these differences. LFP is safer than NMC, but has a flat discharge curve, making state of charge estimation more difficult. LTO can operate at lower temperatures than other chemistries. NMC requires tighter temperature management. The second type is flow batteries, fundamentally different technology. Energy is stored in liquid electrolytes in large tanks. To generate power, electrolytes are pumped through a cell stack, where electrochemical reaction occurs. The biggest advantage, power and capacity, are completely independent. Power depends on stack size, capacity on tank size. This makes them ideal for long-duration applications, storing energy for many hours or days. The most popular flow technology is vanadium redox, VRFB. Lifetime is virtually unlimited, tens of thousands of cycles without significant degradation. But energy density is low, physical size is large, capital cost is high. In practice, used mainly where long duration is critical and space is available. O and M for flow batteries is completely different from lithium-ion. Instead of BMS managing thousands of cells, you have hydraulic systems managing electrolyte flow. Instead of thermal runaway risk, you have electrolyte leakage risk. Instead of cell degradation, you have membrane degradation in the stack. Technicians must be more hydraulic engineers and chemists than electricians. Third type, less common but important in specific applications, is mechanical storage. The largest is PHES, pumped hydro energy storage. Energy is stored as potential energy of water pumped to an elevated reservoir. For generation, water falls through turbines. This is the oldest and most proven storage technology. Some installations have operated for 50 to 60 years. Europe has substantial PHES capacity, roughly 45 gigawatts across the continent. Austria, Switzerland, Germany, Norway all have significant installations. But PHES has limitations, requires specific topography, massive capital investment, years of construction, environmental impact. Few new installations are being built, though modernization of existing facilities is planned. Other mechanical technologies include CAES, compressed air energy storage, storing energy as compressed air in underground caverns. There are a few installations worldwide, mainly in Germany and the US. Flywheel storage stores energy as kinetic energy of a spinning massive disk. Very fast response, virtually unlimited cycles but low energy capacity. Used mainly for applications requiring millisecond response. Frequency regulation. Fourth type is thermal storage. Energy is stored as heat or cold. Could be molten salt, as in CSP solar plants. Could be ice or water. Relatively cheap, long lifetime, but low round-trip efficiency. Used mainly where thermal energy is directly needed, building, heating/cooling, industrial processes. Fifth type, still in development but promising, is hydrogen storage. Energy is used for water electrolysis, producing hydrogen. Hydrogen is stored and later can be burned in turbines or used in fuel cells for electricity generation. Theoretically ideal for seasonal storage. In practice, low round-trip efficiency around 30 to 40%, high costs, technical problems with hydrogen storage. Europe has several pilot hydrogen projects, mainly in the context of heavy industry transformation and transport. But using hydrogen as utility-scale energy storage is still years away, perhaps a decade or more. For O and M operators, the key understanding is that each storage type requires different maintenance approach. You cannot apply the same procedures to lithium-ion as to flow or mechanical storage. They're fundamentally different technologies with different failure modes, different maintenance requirements, different risks. Now let's address the crucial question for understanding storage value. How does it serve grid stabilization, and why are grid operators willing to pay for this service? The electricity grid must be balanced every second. Generation must equal consumption plus losses. If generation exceeds consumption, grid frequency rises above nominal 50 Hz. If consumption exceeds generation, frequency drops. Deviations beyond roughly plus or minus 0.2 Hz cause automatic power plant disconnections and can lead to blackouts. Traditionally, balancing was provided by conventional power plants, coal, gas, which could increase or decrease output. But this is a slow process. A coal plant needs tens of minutes to significantly change power. A gas plant is faster, several to 15 minutes, but still not fast enough for modern grids with high renewable penetration. Energy storage can respond in milliseconds, from 0 to full power in under 1 second, from full charging to full discharging in seconds. This speed makes them ideal for various grid services. First service, frequency regulation or frequency response. The grid operator sends signals every few seconds telling storage how much power to supply or absorb. Storage responds automatically, helping maintain frequency near 50 Hz. Operators pay for this service and, in some countries, very well. In the UK, enhanced frequency response paid at peak moments dozens of pounds per megawatt of available capacity per hour. Prices have fallen as more storage entered the market, but it remains a lucrative segment. Second service, capacity reserve. Storage is on standby to rapidly deliver power in case of unexpected plant failure or sudden demand increase. Most of the time, storage does nothing but wait, but the operator pays for availability alone. Many countries have capacity auctions where storage competes with conventional plants. Third service, energy arbitrage. Buying electricity when cheap, typically at night or midday when solar produces heavily, and selling when expensive, typically evening. This is the simplest service to understand, but paradoxically often not the most lucrative. The spread between lowest and highest electricity price must be large enough to cover efficiency losses, plus battery degradation cost. Fourth service, peak shaving. Large industrial consumers often pay not just for energy consumed, but for peak power, the highest draw in a billing period. Storage can shave this peak, discharging during critical moments. Savings can be substantial. Peak power charges can represent 30 to 40% of a large facility's electricity bill. Fifth service, black start capability, ability to restart the grid after total blackout. Most power plants need external power to start. Storage can provide that power, helping sequentially restore the grid. This is rarely used but critical for energy security. Operators are willing to pay significant sums for black start availability alone. Sixth service, transmission congestion relief. When a transmission line is congested, the operator must pay plants on one side to produce less and plants on the other to produce more. Strategically placed storage can store energy when congestion flows one direction and release it when flowing the other, saving the operator redispatch costs. All these services create a complex ecosystem where storage can participate simultaneously in multiple markets, dynamically optimizing what to do each moment to maximize revenue. This requires sophisticated EMS systems with algorithms forecasting prices, demand, renewable production, and making real-time decisions. For Europe, the prospects are fascinating. Different countries are at different stages of market development. The UK and Germany have relatively mature ancillary services markets where storage competes effectively. Spain and Italy are developing their markets. Central and Eastern European countries are still establishing frameworks. But the trend is clear. As renewable penetration increases across Europe, and it will, driven by climate targets and economics, the need for flexibility increases dramatically. Wind and solar will provide 60%, 70%, perhaps 80% of electricity by 2050. You cannot operate a grid like that without massive storage capacity. It's not optional. Grid operators increasingly view storage as infrastructure rather than just generation. Deploying storage to defer grid reinforcement, manage local congestion, provide voltage support, enhance reliability. This is strategically important because grid reinforcement is slow and expensive. Storage can be deployed in months rather than the years required for new transmission lines. We're seeing this particularly in areas with high renewable concentration. Regions in northern Germany where wind production exceeds local grid capacity. Southern Spain where solar installations are clustered. These areas need either grid reinforcement or storage. Storage is often faster and cheaper. Let's discuss the critical question: what is the actual and potential energy storage market in Europe? The numbers might surprise you. Current state as of late 2024 is substantial, but still a fraction of what's needed. Europe has roughly 30 to 35 gigawatt hours of battery storage installed, not including traditional pumped hydro. This is spread unevenly. Germany leads with about 8 to 9 gigawatt hours. The UK has roughly 6 to 7 gigawatt hours. Italy around 4 to 5 gigawatt hours. Countries like Spain, France, and the Netherlands are rapidly growing from smaller bases. For comparison, the US has approximately 30 to 35 gigawatt hours. China is far ahead with over